Welcome to the lecture series on mathematical modeling, analysis and application. In the last lecture, we have discussed this stability analysis based on this formulation that is like f of x equals to r x into 1 minus x there. So, in this lecture, we will go for like a classification of bifurcation and the basic definition of a bifurcation. And if we will just go for a classification of a bifurcation here, then first we have to know the basic definition of bifurcation, and then like a different class of bifurcations like saddle node bifurcation, transcritical bifurcation and pitchfork bifurcation. So, that stepwise we will just go for the discussion. So, if you will just go for like what do you mean by bifurcation here, and in the last lecture we have represented that we are just going for analysis of a logistic difference equation in like a 2 parametric form or a single parametric form. Then first what we are doing is we are just reducing this 2 parametric values into a single parametric values, and once this logistic difference equation is reduced into a single parametric form, then this representation is written in the form of like r of x n into 1 minus x n as x n plus 1 for different values of r there. So, like for r equals to 2.5, we have just find that initially it is just taking a peak variation or a sharp variation, then after that there is a stable achievement it has just obtained, and we are just saying that the behavior is stable in that phase. And for r equals to 3.3 and 3.33, we have just find that the behavior is periodic with period 2. But for r equals to 3.9, we have just to find that the behavior is chaotic. This means that irrespective of the position or time, it is just behaving erratically there. This means that maybe sometimes it is just taking 4 oscillations or 8 oscillations, sometimes 16 oscillations. It does not depend on the initial value or how it is just behaving afterwards, it does not matter. So, other than this stable nature, a small change in model parameters may lead to a significant changes in the solution behavior. Sometimes what we are doing is to obtain a steady solution, we have just added some small parametric values in the solution process to accelerate these values, and finally we can just obtain a stable solution. And this phenomenon of very significant changes in solution behavior, whenever we will just take a small changes in the model parameter, then we can obtain the bifurcation there. And the critical values of model parameter where this phenomena is occurring is called bifurcation points. So, especially to determine this bifurcation points, so different formulations or methods it has been used also. But if you will just go for like classification of bifurcation, there are 3 basic canonical types of bifurcation occurs in the first order difference equations. So, first one it is called saddle node bifurcation, and second one is called transcritical bifurcation, third is called pitchfork bifurcation. And the question arises that why they are called canonical, since its behavior it looks to be a canonical sense, it is just occurring inside the system. So, first they are experienced by higher order difference equations also. So, it is not matter that we are just considering only first order difference equation and we can have a bifurcation, but for like higher order equations the bifurcation also exists. And other bifurcations if you will just consider, we can just take this is a slight modification or it is just a combination of these 3 bifurcations at best we can just say. So, whatever this classical bifurcations, so we can just find or we are just seeing in the nature, they are basically classified into 3 sections or 3 types, but all other bifurcations especially people are deriving by combining these 3 bifurcations in different forms. So, first we will just go for a saddle node bifurcation here, and a prototype equation for saddle node bifurcation is written as yn plus 1, this as yn minus yn square plus mu. This is generalized formulation of a saddle node bifurcation and to give like a first introductory note about the saddle node bifurcation. So, people are using this basic equation, and if you will just see this function y n plus 1, which involves the terms like y n and mu here. So, completely we can just say that this is nothing but a function of y n and mu as y n plus 1. In general, a saddle node bifurcation occurs near the bifurcation point. Since already I have told that when this system behaves theoretically at a point, then that point is called bifurcation point. And if the model possesses an unique curve of fixed points in the y mu plane, then we can just find this bifurcation nodes. And this curve lies on one side of the line, like mu equals to mu c, where mu c represents the critical value of mu and passes through bifurcation points. And the steady states of for this equation, like y n plus 1 equals to y n minus y n square plus mu, which can be obtained if you will just replace y n plus 1 as y n, this equals to lambda. Already we have used this one as a fixed point function form, or where a function is like a fixed point, we can just say that f of x equals to x there. And in that sense, if you will just use this lambda in terms of y n plus 1 and y n here, this equation will be reduced as lambda. Since y n plus 1, it can be written as lambda here, y n can be written as lambda here, y n square it can be written as lambda square plus mu. And if you will just see, then lambda it will just cancel it out, we will have the terms like lambda square equals to mu. So, that is why lambda can be written as plus or minus square root of mu. And clearly this equation, or this equation represented as a prototype equation for saddle node bifurcation, has no steady states for mu less than 0. Since if it is a negative number, then we cannot say that it has a steady solution. And plus or minus square root of mu for mu greater than, it is just existing a solution there. Also, the positive steady state is stable and negative is unstable. So, this means that if you will just take this derivative, that is f dash of y n mu, if you will just take the derivative, then we can just write this one as like first derivative with respect to y n we are just considering here. This means that 1 minus 2 y n plus mu if you will just consider, and we can just proceed, then we can just find this stability condition there. So, if you will just go for like a picturization sense, the bifurcation point is at y c mu c, which is called critical points, which is existing at 0 0 point, and the graph of lambda equals to plus or minus square root of mu is a parabola opening rightward, and the eigenvalue corresponding to this bifurcation point is 1 here. And the conditions for such bifurcation to occur are like, first we will just consider this functional value equals to 0. Then if you will just take the first order derivative with respect to y sense, so then this will just take the value as 1 there. And if you will just take this differentiation with respect to mu for this function, this will be not equals to 0, and if you will just take the second order differentiation with respect to y, this will also not equals to 0. So, these are the conditions it should be justified to get this bifurcation points. And for example, if you will just consider like a insect pest model, then we can just find that this bifurcation where it is just starting or occurring. So, if you will just go for like a second bifurcation here, that is a transcritical bifurcation, the prototype equation is considered as like y n plus 1 equals to y n minus y n square plus mu y n here. So, from the last equation if you will just see here, so we have just multiplied only with y n term with mu term here, which is obviously a like a complementary function of like function of y n and mu. In general, a transcritical bifurcation occurs near the bifurcation point. Since bifurcation starts at a point, so that point is considered for all these bifurcation levels. And if the model possesses two curves of fixed points in the y mu plane, then we can just say that it is a transcritical bifurcation. And if both these curves pass through this bifurcation point, that is y c mu c, we will have like critical point for y and critical point for mu, and both lie on the both sides of the line mu equals to mu critical, then we can just say that this bifurcation is occurring. Clearly it has two steady states. If you just see, that is lambda equals to 0 is trivial and lambda equals to mu, it will just give you a non-trivial sense here. This means that directly yn plus 1 is replaced by lambda and yn is also replaced by lambda here. So, then the complete equation will give you as like lambda, this equals to lambda minus lambda square plus mu lambda here. And if this will cancel it out, this implies that we can just write lambda square minus mu lambda, this equals to 0. This implies that lambda into lambda minus mu, this equals to 0. Obviously, we can just write lambda equals to 0 or lambda equals to mu here. So, based on these two values, we can just say that we will have a like a trivial solution or a non-trivial solution. For stability of a steady state, that is, if you just assume here f dash of lambda mu as, like if you just take the difference here, we will have like 1 minus 2 lambda plus mu here. The difference of like f, it can be written as like f of lambda mu, which can be written as like lambda minus lambda square plus mu lambda here. And if you just take the derivative with respect to lambda here, f dash of lambda mu, so which can be written as like 1 minus 2 lambda plus mu here. And the trivial steady state is like stable if mu less than 0 and non-trivial is stable if mu greater than 0 here. And if you just go for the like a graphical sense of transcritical bifurcation here, the bifurcation point is at y critical and then mu critical, which is occurring at 0 0 point here. Both the graphs y equals to 0 and y equals to mu, if you just consider, are the straight lines here, and exchange of the stability occurs at bifurcation point, and conditions of such bifurcation to occurring or to occur are like f y critical and mu critical point, the function should take the 0 value. And if you will just consider like first order derivative of f at these critical points, this should take the values as 1 here. And if you will just take this derivative with respect to mu at these critical points, this will also take the 0 value there. And if you will just take the second order derivative of this function at these critical points, this will not equals to 0 there. So, if we will go for like pitchfork bifurcation, this is the last bifurcation we want to discuss here. The prototype equation for pitchfork bifurcation is like yn plus 1 equals to yn minus yq plus mu yn here. So, if you just see our previous this prototype equations, here we have extended one power, that is yn minus yn square is the basic terms we have just considered for the last two prototype equations, but here we have just extended as a power 1 here, and rest is like the previous bifurcation we have just discussed, that as transcritical bifurcation, the same terms it is just present here, yn and mu yn, which is especially represented as a functional value, that is f of yn and mu here. And in general, a pitchfork bifurcation occurs near the bifurcation point, whatever it has observed for the like last bifurcation methods or the classification of bifurcations. And if the model possesses two curves of fixed points in the y mu plane, then we can just say that it is pitchfork bifurcation. Both these curves pass through bifurcation point, that is the critical points y c and mu c, and one of which lies on the sides of the line mu equals to mu critical point. Clearly, if you will just see here, so we will have this steady states, that is in the form of lambda equals to lambda minus lambda q plus mu lambda here. Since we are just replacing yn plus 1, this as yn equals to lambda here. And if you will just see here, this implies that lambda q minus mu lambda, this equals to 0. Obviously, we can just write lambda into lambda square minus mu, this equals to 0, and we can just consider either lambda equals to 0 or lambda square equals to mu there. And if you will just find the root here, lambda equals to plus or minus square root of mu. And like 3 values we can just get it over here. So, for lambda equals to 0 we will have a trivial solution, for lambda equals to plus or minus square root of mu we will have a non-trivial solution here. And if you will just take the derivative of this equation here, that is nothing but f of lambda mu, which can be written as like f of lambda mu as lambda minus lambda q plus mu lambda here. And if you will just take the derivative with respect to lambda here, which can be written as 1 minus 3 lambda square plus mu here, this equals to 0. And the trivial steady state is stable if mu less than 0 here. This means that we can just assume that if lambda equals to 0, first condition if you will just see here, then 1 plus mu we can just get it over here. And the trivial steady state is stable whenever we can just consider mu less than 0, means we will have like f dash of lambda mu, it should be less than 1 in absolute sense. And both non-trivial steady states are stable if mu greater than 0 here. Since obviously if you will just consider like lambda equals to plus or minus square root of mu here, then we can just find it is stable for all mu positive values there. So, if you will just go for analysis of pitchfork bifurcation in a graphical sense here, then we can just find that the bifurcation point is at yc mu c, that is the critical point which is just observed at 0 0 here, and the graphs y equals to 0 and y equals to plus or minus square root of mu are respectively straight lines, if you will just see. So, and parabola opening, it is just opening towards the rightward here, and exchange of stability occurs at the bifurcation points, that is at 0 0 point here. And conditions for such bifurcation to occur are like if you will just consider this critical point, the functional value is 0, and if you will just take the first order derivative with respect to y as 1 here, and if you will just take this first order derivative with respect to mu, this is nothing but yc mu c, this equals to also 0. If you will just consider also the second order derivative with respect to y, yc mu c, that is at critical point, this will also take the 0 value here. And if you will just take the mixed derivative, that is f of y mu at these critical points, that is yc mu c, this is not equals to 0. And for this case we can just consider as the third order derivative with respect to y as also not equals to 0, since yc mu c it is not equals to 0. If you will just visible this graph of lambda equals to plus or minus square root of mu, which is expanded towards rightward here, which completely shows the pitchfork bifurcation in a complete sense here. So, in this lecture, first we have discussed the basic definition of bifurcation, where we have defined that where this bifurcation starts by considering the example, that is in the form of like if you will just see xn plus 1 equals to rxn into 1 minus xn, which is the reduced parametric equation from like a 2 parametric form to the single parametric form in the non-dimensional sense. And there itself we have just to find like for a particular value like 2.5 we have just obtained a steady solution, and for like 3.3 and 3.33 we have just obtained that we will have a like periodic solution. But for 3.9 we have just find a chaotic nature. So, it is very essential to find a point where this chaotic nature has been started, especially that point is called our bifurcation point after like putting certain perturbation values there. So, based on that we have just defined this basic definition of a bifurcation start, and then we have started about like the classification of bifurcations. So, we have just discussed that 3 types of bifurcations, it is just basic uses by the like people who are working on that direction, and especially nowadays people are using like a different class of bifurcations by modifying this 3 direct bifurcation methods, either by combining them in a together form or sometimes some modifications they are just doing. And these three complete bifurcations, whatever it is, has been majorly used, that are defined as saddle node bifurcation, transcritical bifurcation, and pitchfork bifurcation. And in point wise, we have just started about saddle node bifurcation. In the saddle node bifurcation, we have just considered like a basic equation that is used in a like prototype equation, which is defined as yn minus yn square plus mu. And if there is a little modification of this equation, it has been taken, which is considered in the form of like transcritical bifurcation, where this mu is multiplied with a variable term in terms of yn there. And if we are just going for the pitchfork bifurcation, then there is a power change in the yn term in the second case there from this transcriptive bifurcation only. And based on this, we have just find that the difference of three bifurcation methods, that is saddle node bifurcation, transcritical bifurcation, or pitchfork bifurcation there. And then we have just put these values to find this logistic difference equation, which is explained as xn plus 1 equals to rxn into 1 minus xn. And that we have just expressed in the last lecture to find this like periodic doubling or flip bifurcation, how it is just occurring there, that we have just considered. And usually the typical form of the same is given in the form of like yn plus 1 equals to minus yn plus yn cube minus mu yn, which is defined as functional values as like f of yn mu. And you can observe that here on the right hand side, the function of equation 8.5 is a negative of the same of the pitchfork bifurcation. Thank you for listening this lecture.